Namaskaram. Today also we will see some properties of Fourier transform. In last class we have seen the linearity property and shifting property of Fourier transform. Okay, third property, if f of x is even function in minus infinity to plus infinity, that means an entire real number, then Fourier transform of f of x is equal to Fourier cosine transform of f of x. So naturally f inverse is equal to fc inverse. Okay. So by definition, what is Fourier transform of f of x? Yes, by definition, this is the definition of Fourier transform 1 by root 2 pi integral minus infinity to plus infinity f of x e raised to minus I omega x dx. Okay. Next, we are going to replace this e raised to minus I omega x using the rule e raised to I theta equal to cos theta minus I sin theta. Okay. So what happened? So this become cos omega x minus I sin omega x. Okay. Then next we just expand this integral using this plus sign, so this minus sign. So now we have two different integrals. So first integral is 1 by root 2 pi integral f of x into cos omega. The second one is I by root 2 pi, that's a constant, and the remaining time is integral f of x into sin omega x dx. Okay. Okay, now here it is given that f of x is even function. Okay, so this function is even. And what about cos? Cos function is also even. So even into even. We know that even into even again even. Okay, so this integrand is even. And what about the second integration? In second integration, here f of x is even, that is given. And we know that sine is odd function. Okay, sine is odd function. So even into odd is nothing, it is odd function. And here this integral is of the form integral minus a to plus a, and we know that integral minus a to plus a an even function, that's equal to 2 times integral 0 to a. And similarly integral minus a to plus a odd function is equal to 0. Okay, so in the case of first part, this integration become 2 times 0 to infinity, and in the case of second part, this integration becomes 0 because this entire integrand is odd function. Okay, so this integration become 2 by root 2 pi integral 0 to infinity f of x cos omega x dx minus 0. This part is 0. Now you can cancel 1 root 2, so this become numerator become root 2 and denominator is root pi. So combining these two, we get square root of root 2 by pi integral 0 to infinity f of x cos omega x dx. And what about this function? What is this? Yes, this is exactly our Fourier cosine transform of f of x. This is our Fourier cosine transform of f of x. So that's why if f of x is an even function, then Fourier transform is same as Fourier cosine transform. Clear? Okay, as a direct consequence, by the definition of inverse function, it is clear that their inverses are same because the transformations are same, so inverses also naturally same. So for taking f inverse, suppose we know the original function is even. If you know the original function is even, then instead of f inverse, you can apply fc inverse for your cosine inverse. Okay. Fourth property, if f of x is odd function in entire real number, then f of x, Fourier transform of f of x is equal to minus I into fs of f of x. Similarly, f inverse is equal to I into fs inverse. Okay, so first we are going to prove this result. Okay, this is the definition of Fourier transform. So we just expand the series to minus I omega x as similar to the previous problem. Then we just expand this in bracket and expand this integration as two integrals like this. Then what happened? As similar to the previous case, here f of x is odd function, this is even function, so product is odd function. Okay, it's an odd function. And similarly here f of x is odd function, this is also an odd function, so the product is even function. Okay, so in the case of this first integration, this is 0 because integration of odd function from minus infinity to plus infinity. Here it's an even function. The product function is even, so this become 2 times 0 to infinity. Okay, and you can cancel this one root 2. So upon simplification, we get minus I into square root of 2 by pi 0 to infinity f of x sine omega x dx. And what about this portion? After I, this portion is nothing our Fourier sine transform. That's why this is equal to minus I into fs of f of x. Okay. Okay, this is the graphical representation of this result. That means suppose our function is f of x and you consider the Fourier transform of this function. Here we assume that this f of x is odd function. Okay, that's our assumption. This is the Fourier transform. We denote by f cap of omega. Then by this, actually this is our f cap of omega. Okay, and this result says that we can find this f cap of omega using this rule. What is this rule? Minus I times fs cap of omega. So first you find the fs cap of omega, that is nothing our Fourier sine transform. Then we multiply that fs cap of omega by minus I. That's give f cap of omega. So you can find this f cap of omega either this way or this way. Okay, that's the idea. Now we are ready to find derive this second portion. That is very easy. So our aim is to find this f of x from this f cap of omega. Either you can directly take f inverse. Okay, that is one method to find. One second. That means we can directly take f inverse from this f cap of omega using the definition of inverse Fourier transform. Okay, that is what? That is nothing. That is f inverse of f cap of omega. We can also find this inverse using this route. You can use this path. Okay, so what is the idea? First we have to find fs cap of omega from f cap of omega. How? Because there is a simple relation between fs cap of omega and f cap of omega. This is the relation because f cap of omega equal to minus I times fs cap of omega. That's a relation. Okay, if you have a Fourier sine transform, then you just simply multiply this Fourier sine transform with the minus I, that give f cap of omega, provided f of x is odd function. Okay, so first we have to remove the effect of this minus I. How? By divided by minus I. So this fs cap of omega, that means this quantity, that is equal to 1 by minus I into f cap of omega. Okay, that is very easy. We simply divide this quantity by 1 by minus I, that give fs cap of omega, or you can directly from this relation. Anyway, and also we know that 1 by I. What is 1 by I? Yes, 1 by I is minus I. So there is a one more minus sign. So minus into minus plus. So this become I into f cap of omega. So this fs cap of omega is nothing. It is I into f cap of omega. Then how to find this f of x? You simply take f inverse. Not f inverse. We simply take fs inverse. So to find this f of x, we just consider fs inverse of this quantity. That is a process. Okay, so this inverse is, we can evaluate this inverse using this way. That is, this is equal to fs inverse of fs cap of omega. If you take the Fourier sine inverse of fs of omega gives same function, and just we replace this fs cap of omega using this I into f cap of omega. Okay, so we just replacing I into f cap of omega. And also we know that Fourier transform and inverse transform both are linear. Okay, they are we can represent this Fourier transform and Fourier sine transform using integrations. So they are linear. So you can take this I outside. So this become I into fs inverse of f cap of omega. So what is the conclusion? This f inverse equal to I into fs inverse. That's the idea of this portion. F inverse is equal to I into fs inverse. Okay, this function e raised to minus k into x square is an even function. Okay, because if you're replacing x by minus x, there is no change. So this is an even function. And we know that the Fourier transform of e raised to minus kx square is equal to 1 by root 2k e raised to minus omega square by 4k. We proved this result in our lecture 6. Okay. By our result number 3, and this function is even, so the Fourier cosine transform of f of x is same as Fourier transform of f of x. If it is if f of x is even, here this function is even. So as a consequence of this result, Fourier cosine transform of e raised to minus x square minus kx square is equal to the same result, 1 by root 2k e raised to minus omega square by 4k. Okay, in particular, the Fourier cosine transform of e raised to minus x square by 2. Okay, to get this result, what is the value of k? To get this e raised to minus x square by 2, what is the value of k? Yes, if you choose k is equal to 1 by 2. If you choose k is equal to 1 by 2, this becomes e raised to minus x square by 2. So what about the right hand side? The right hand side, if k is equal to 1 by 2, this term is 1. So e raised to minus omega square by 4 into 1 by 2, that is 2. So this is omega square by 2. So that's why this is equal to Fourier cosine transform of e raised to minus x square by 2 equal to e raised to minus omega square by 2. Okay. We used this result in example 2 of our lecture 4. Okay. Consider this problem. When the Fourier transform of f of x is equal to 1 minus mod x if mod x is less than 1, 0 otherwise. Okay, what is mod x less than 1? Mod x less than means nothing, it is minus 1 less than x less than 1. Okay, so in this interval our function value is 1 minus mod x. Outside this interval function is always 0. Hence evaluate integral 0 to infinity 1 minus cos x by x square dx. So first we have to find the Fourier transform of this function. What is the definition of Fourier transform? Okay, either you can apply the direct Fourier transform formula. Another interesting thing is here this function is even, because if you're replacing x by minus x, there is no change, isn't it? If you're replacing, if you suppose you consider f of minus x, what happened? This is 1 minus modulus of minus x whenever mod x less than 1. There is no change, always 0 whenever mod x otherwise there is mod x greater than or equal to 1. So what about modulus of minus x? That is 1 minus still mod x. Modulus of minus x is same as mod x. So ultimately this is nothing, this is same as our f of x. So here f of minus x is same as f of x. That's why this function is even. So we can use the property of Fourier transform. If a function is even, then we know that the Fourier transform is same as Fourier cosine transform. So instead of finding Fourier transform, here we use the formula of Fourier cosine transform. Okay, what is the formula of Fourier cosine transform? Yes, so our Fourier transform is denoted by f cap of omega. That is equal to Fourier cosine transform. This is the formula of Fourier cosine transform. And also it is clear that this function is exist in the interval minus 1 to plus 1. Our range of integration is 0 to infinity. So in the case of 0 to infinity, our function is non-zero only in the interval 0 to 1. After that our function value is 0. Okay, that's why we consider the integral 0 to 1. So in the 0 to 1, what is our function? Our function is nothing, function is 1 minus mod x, and but in this range our x is positive. Clear? Since x is positive, what about mod x? Mod x is same as 1 minus x, because mod x is same as x. Okay, so our function is 1 minus x. Over the interval 0 to 1, our 1 minus mod x become 1 minus x, because mod x is x itself into cos omega x dx. Next we are going to apply the Leibniz rule of integration by choosing this is our first function, this is our second function. Okay, otherwise you can apply the integration by parts 2 times. Anyway, this integration become first function into integral of second minus derivative of first one, that is minus 1, into integral of this portion v2 means integral of v1, integral of this one, that is minus cos omega x by omega square. Okay, next you have to apply the upper limit and lower limit. So this become Okay, if you substitute x equal to 1, this term becomes 0. 1 minus 1, 0. That's why first term is 0. When x equal to 1, this term becomes cos omega by omega square. And what about the sign? We have 3 minus sign, minus, minus, minus. So minus. So minus cos omega by omega square. Minus, next we are going to substitute the lower limit. When x equal to 0, here one term is sine 0. Sine 0 is 0. Again, the first term is 0. And when x equal to 0, this become 1 by omega square. And what about the sign? Similar to the previous case, minus, 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 3 minus sign is there, so minus of 1 by omega square. Okay, so by expanding this bracket, this term become plus. So combining these two, because their denominators are same, so you can combine these two. So this become root 2 by pi 1 minus cos omega by omega square. So this is the Fourier transform of this function. Actually, we use a property. We evaluate the Fourier cosine transform. We know that the Fourier cosine transform and Fourier transform of a even function is same. That's why we use this formula. Anyway, this is the Fourier transform. Next, we have to evaluate this integration. Okay, how to find this integration from this Fourier transform? Okay, so this is our Fourier transform f cap of omega. To find this integration, we consider the inverse Fourier transform of f cap of omega. We simply consider the inverse Fourier transform of this f cap of omega. And what about this inverse Fourier transform of f cap of omega? That depends the continuity of the function, given function f of x. Here, this is the graph of this function. Over the interval -1 to +1, the 1 minus mod x, this is like a triangular shape. And after that, the function value is 0. Okay. Anyway, it is clear that this function is continuous everywhere. Continuous everywhere. When x equal to 0, its value is 1. This is 1. And when x equal to 1, its value is 0. Clear. Similarly, when x equal to -1, also 0. Anyway, this is the shape of this function. And this is continuous everywhere. Since it is continuous, from our remark 1 of the definition of Fourier transform, this f inverse of f cap of omega is nothing, it is exactly f of x. Very important. Okay, this is due to the continuity of the function, given function f of x. This function is continuous. So you can use this result. So f of x is equal to f inverse of f cap of omega. And from our third property of the Fourier transform, our f inverse is same as fc inverse because this function is even. Because this is even. So we can use this result. F of x is equal to fc inverse of f cap of omega. And what is the formula of inverse cosine transform? You can apply the formula of inverse cosine transform on this f cap of omega. F cap of omega is nothing, this function. Okay, so this become root 2 by pi 0 to infinity f cap of omega into cos omega x d omega. So this is the formula of inverse Fourier cosine transform. Okay. Next we are going to just replace this f cap of omega by this function. So this integration become, so this is root 2 by pi 0 to infinity. And what is f cap of omega? This function root 2 by pi 1 minus cos omega by omega square and cos omega x d omega. Okay. Now you can this root 2 by pi is a constant, you can take outside, and comparing these two, this become 2 by pi. And so this become, so f of x is equal to, comparing these two, 2 by pi 0 to infinity 1 minus cos omega by omega square cos omega x d omega. Okay, now we are ready to evaluate this integration. Okay, now we are ready to evaluate this integration. Yes, which value of x gives this integration? You think about this right hand side, and which value of x gives this integration? Yes, that is x equal to 0. You substitute x equal to 0, this portion is almost similar to this integration. Okay, so you simply substitute x equal to 0 on throughout. So what happened? F of 0 equal to 2 by pi 0 to infinity 1 minus cos omega by omega square. When x equal to 0, this term is 1. So d omega. Okay, so what is f of 0? It is very clear from this function. 0 is here. So f of 0 is what? When x equal to 0, f of 0 equal to 1. So LHS become 1. Okay. So you can write 1 is equal to, okay, so 0 to 2 by pi, 0 to infinity, 1 minus cos omega by omega square d omega. So just multiply this pi by 2 on left hand side. So this become pi by 2 equal to 0 to infinity, 1 minus cos omega by omega square d omega. So our required integral is equal to pi by 2. Okay. Yes, that is equal to pi by 2. This is your homework. Thank you.